Hello students, now we will solve some problems on DC motor. So, I will consider the examples of DC series motor and also the shunt motor. So, now you see that when we are doing the problems, first I already told you many times, first you see that what type of motor it is. So, first you collect, you see that and decide that what type of motor, and then the equations pertaining to that. Okay, collect the data given in the problem. Okay. So, now I am going to solve, today I am going to solve the problems on DC series motor and shunt motor. So, in this, when we are going to consider the connection, in case of series motor, the armature is connected in series with the series field winding. This series combination is supplied by the voltage source V. Then the current I is drawn by this supply, and then I is equal to ISE, that is equal to IA. So, the internal resistance of the armature, if we are going to consider it is RA. So, when we are going to consider this shunt motor, this armature is connected in parallel with the shunt field winding. In this, the supply voltage V we are considering is plus minus with the polarity, and then current drawn by the armature or motor is I, and according to KCL, this current is divided into two parts, that is current flowing through the shunt field winding and the current flowing through the armature. RA represents the internal resistance of the armature. So, now this is EB, the back EMF developed, the back EMF opposes the supply voltage, and the equations pertaining to this, what we are considering mainly is the IA is equal to I is equal to ISE. Since all are connected in series, the current drawn by the armature from the supply I is equal to the armature current is equal to the series field winding current. So, now EB is equal to, means the back EMF induced is V minus IA RA plus RAC, because both are connected in series. And then we have one more equation, EB is equal to Zn phi p divided by 60A. And we have two equations for torque, that is 0.159 Z phi Ia Newton meter, or we will consider it is Ta is equal to the output EB Ia divided by N Newton meter. Okay. And also we have equation for TSH, that is equal to output by N. So, this is also in terms of Newton meter. When we are going to consider this shunt, we do not have the series in this equation. When we are going to consider this shunt motor, EB is equal to V minus IA RA, and then current ISH is equal to V divided by RSH. These are the main equations we are considering when we are doing the problems on series motor and shunt motor. Okay. First you see that in this problem, it is 4 pole 250 volt series motor has a wave connected armature with 200 conductors. The flux per pole is 25 milliweber when the motor is taking a 60 amp, means the current drawn by the motor is 60 ampere from the supply. Armature resistance is 0.15 ohm, while the series field resistance is given it is 0.2 ohm. Since the series field winding is connected in series with this armature, the resistance value is very less. Suppose if you have connected that shunt field winding, that will be more, it is more than 100 ohm, it is around 200 ohm we are going to consider. Okay. So, here collect the data given, here in this the supply voltage given is 250 volt, the number of poles is equal to 4, since it is wave connected motor, the number of parallel paths is equal to 2, the number of conductors given is 200, the flux per pole is 25 milliweber, so it is 25 into 10 to the power minus 3 Weber. Then current drawn by the motor is 60 ampere, since the series field winding is connected in series with the armature. So, IA is equal to IL is equal to ISC, that is 60 ampere. The resistance of the armature is 0.15 ohm, RSC is 0.2 ohm. Now, what exactly you have to calculate? Calculate the speed of this motor. Okay. So, now to get this speed, so we have to use this equation, EB is equal to Zn phi p divided by 60A. When we are considering this, EB is also unknown, here N is also unknown, two unknown parameters are there in this. That is why you use this one more equation to calculate this back EMF, EB is equal to V minus IA. Since it is series, you have to add the resistance, that is armature resistance and series field resistance. So it is V minus IA multiplied with the sum of RA plus RSC will give you this EB. Substitute the value of this back EMF in this equation, get the value of the speed of the armature or motor, that is what we are getting is 1374 RPM. This is how you have to perform. So next, you consider one more example of DC series motor. It is running with a speed of 800 RPM while taking a current of 20 ampere from the supply. If the load is changed, you observe in this, here the load is changed such that the current drawn by the motor is increased to 50 ampere. In the last class, when I was explaining that characteristic of DC series motor, I told you that as the speed increases, what will happen? The load decreases, or when the load increases, the speed decreases. It is vice versa, because the load is inversely proportional to speed, or speed is inversely proportional to load. So now you have to calculate the speed when the load current, the current drawn by the motor is increased to 50 ampere. The armature and series field winding resistance is given, that is 0.2 ohm and 0.3 ohm respectively. Now assume the flux produced is proportional to the current. In series connection, always we will consider that flux produced is directly proportional to the current. Assume supply voltage is 250 volt. Collect the data given. So here I already showed that how exactly we are drawing that series field connection, that is series field winding is connected in series with the armature. So this type of motor we are going to consider it is series motor. Okay. So collect the data given. For the first condition, the speed is given, that N1 is equal to 800 RPM, and when we are considering this speed, the current drawn by the motor is 20 ampere. So in the second condition, the current drawn by the motor is 50 ampere. Under this condition, we have to calculate the speed of the motor. The supply voltage given is 250 volts, the resistance of the armature given is 0.2 ohm and series resistance is given as 0.3 ohm. So we know that V, that is our supply voltage, has to overcome the back EMF and the drop. Okay. V is equal to EB1 plus IA1 RA plus ISC RSC, because both are connected in series. This V is equal to EB plus IARA plus ISC RSC. Since this all are connected in series, I is equal to ISC is equal to IA. Use this relationship in getting the value, that is EB1. Okay. You know the value of V, substitute it is 250 volts. You know IA1 is 20 ampere, RA you know it is 0.2 ohm, ISC is same as this IA1, RSC you have this 0.3. So substituting and calculating the value for this EB1, we are getting it is 240 volts. Then for the second condition, as the speed increases, what will happen here? I had written here EB is equal to Zn 5P divided by 60A. So when the load increases, the speed decreases, means when the load varies, always the speed varies. When the speed varies, this back EMF also varies, because EB is directly proportional to speed. So now you will get that different value of this EB2 for the second condition. You calculate that. Now you have for the second case, V is equal to EB2 plus IA2 RA plus ISC RSC. By using this equation, so now you calculate this, V is given, so that is 250 volts as prior to that. Okay. IA2, now it is changed from 20 ampere to 50 ampere. Now IA2 is 50 ampere, RA is fixed. So now since both are connected in series, RA and RSC, so IA2 is equal to ISC2. So substitute the value, get the value of this EB2, that is 225 volt. EB1 is 240 volt, EB2 is 225 volt. Now use the relationship, that is N is directly proportional to EB by 5, because in this relationship, when you are going to calculate, when you are going to consider the equation for speed, that is EB divided by, you have Zn. So N you are going to calculate Z5P, it is into 60A. Now you see that N is directly proportional to EB by 5. N is inversely proportional to 5 and is directly proportional to EB. So, by using this relationship, and also we know that in case of series motor, phi is directly proportional to IAC, that is directly proportional to IA. So, now when you are going to consider this, we will have that for both the conditions, when you are considering this first speed, it is N1, in the second case it is N2. So, you have N1 by N2 is equal to EB1 divided by EB2 multiplied with phi 2 divided by phi 1. Since this phi is directly proportional to IA, so this phi 2 is directly proportional to IA2 and phi 1 is directly proportional to IA1. So, you know the value of IA2 and IA1, you know the value of EB1, EB2, you have calculated this back EMF for the first condition and also the second condition. You know the speed N1. Now, only thing what you have to calculate is N2. So, under this condition, we have got this N2 is equal to 300 RPM. See that? So, here N1 is equal to, we have, in the first case N1 is equal to 800 RPM. Under this condition, IA1 or the load current, that is the current drawn by the motor is 20 ampere, and then IL is increased to 50 ampere. Now, what is this N2? N2 is equal to 300 RPM. See now, when the load current is less, the speed is more. When the load current is more, the speed is less. What is the meaning of this? Here, the speed is inversely proportional to phi, or since phi is directly proportional to current, it is directly proportional. So, now the speed is inversely proportional to current, means the speed is inversely proportional to load. So, that is why as the speed increases, the load decreases, as the load increases, the speed decreases. Next, you see the problem in this condition, they did not mention which type of motor it is. So, here they mentioned only it is a DC motor, it is of 220 volt supply voltage, armature resistance is 0.75 ohm, it is drawing an armature current of 30 ampere, driving a certain load, the load is not mentioned what type of load it is, calculate the induced EMF of the motor under this condition. So, here to get that induced EMF, it is not necessary to mention any type of motor, here it is mentioned it is DC motor. So, under this condition V is equal to EB plus IARA, since only RA is mentioned, so you can see that it is a shunt motor. Okay. In this data itself you can see that it is a shunt motor. If it is RSA is mentioned, this you can consider it is a series motor. Since only RA is mentioned, you can think that it is a shunt motor. You have the equation, that is V is equal to EB plus IARA. So, from the given data, so after substituting all the values, that is V, IA, RA, you can calculate this EB. It is very easy to calculate this EB. So, EB is equal to, now it is 197.5 volts. Similarly, it is not necessary always to mention any type of motor. So, you see the data given in the problem and then you analyze that which type of motor it is, then you start doing the problem. So, here also in this problem also the type of the motor is not mentioned. The data is given as it is a 4-pole DC motor, it has lap connected armature winding. Lap connected armature winding is number of parallel paths is equal to number of poles. So, P is equal to 4 now, A is equal to 4. The flux per pole is given as 30 milliweber, it is 30 into 10 to the power minus 3 Weber. The number of armature conductors is mentioned, it is 250. When connected to 230 volt DC supply, it draws an armature current of 40 ampere. Calculate the back EMF and the speed with which motor is running, assume armature resistance is 0.6 ohm. So, since the speed is directly related to EB, first you calculate that EB by using the voltage equation. Okay, for a motor we have V is equal to EB plus IARA. Since RSA is not mentioned, only RA is mentioned, you can think that it is a shunt motor. So, for shunt motor V is equal to EB plus IARA, we have this voltage equation. Substitute this V and also IA given, that is 40 amps, and then RA 0.6 ohm. Okay. So, when you are calculating, you will get that EB is equal to 206 volts. And we have the relationship between EB and speed in this way, that is the generated EMF equation EB is equal to Zn phi p divided by 60A. When you are substituting all the values, you can calculate this N, that is what we are getting is 1648 RPM. You see the next problem, this is also in this problem also, they did not mention that which type of motor it is, only the data is given. So, it is 4 pole DC motor, P is equal to 4. So, and then it takes 50 amps armature current, IA is equal to 50 ampere. The armature has lap connected, means the number of parallel paths is equal to P, that is equal to 4. The number of conductors Z is equal to 480. The flux per pole is given 20 milliweber. Now, we have to calculate the gross torque developed by the armature of the motor. See here, they have mentioned it is gross torque developed by the armature of the motor, means you have to calculate that TA. We have the equation TA is equal to 0.159 phi Z IA multiplied with P by A Newton meter. So, you substitute all the values, phi is given, it is 20 milliweber. So, it is 20 into 10 to the power minus 3 Weber. The number of conductors is 480. Then the armature current IA is equal to 50 ampere, it is mentioned in the problem. So, P is given as 4, since it is lap connected. So, the number of parallel paths A is equal to number of poles, that is equal to 4. Substituting all these values, we will get this TA, that is gross torque developed by the armature of the motor is 76.394 Newton meter. So, now without mentioning this, also we can analyze the motor circuit, what type of motor it is. So, next in this problem also they did not mention which type of motor it is. It is a 4 pole lap wound DC motor, it has 540 conductor, its speed is found to be 1000 RPM when it is made to run light. See here, we have used that new word here, it is running light. Running light means it is going to run at no load. So, without considering the load, it is, you are going to consider it is on no load condition. The flux per pole is 25 milliweber. It is connected to 230 volt DC supply. The armature resistance given is 0.8 ohm. Now, we have to calculate the induced EMF and armature current. So, now collect the data given. In this problem, the number of poles given as 4, A is equal to P is equal to 4 per lap connected winding, Z is equal to, so here they have mentioned the number of conductors is equal to 540, the flux per pole is 25 milliweber, so 25 into 10 to the power minus 3 Weber, the supply voltage V is equal to 230 volt, RA is equal to 0.8 ohm. I already told you that running light load means it is on no load condition. So, now you consider the speed given, that is 1000 RPM when it is made to run light, you are considering the no load speed is 1000 RPM. So, now the EMF generated, we have the equation EB is equal to Zn phi p divided by 60A. So, substituting the value of Z, then N0, phi and P divided by 60 into number of parallel paths, you get me the value, that is EB0. So, the EB0 after substituting the recovered values in the generated EMF equation, we are getting EB0 is equal to 225 volt. So, now what is the aim of our problem here? Calculate the induced EMF, you have calculated the induced EMF, then you have to calculate this armature current. So, armature current and induced EMF is related in this equation. For a motor, we have the supply voltage is equal to induced EMF plus the voltage drop across the armature. Substitute the EB0, we have calculated already, that is we have the 225 volt. So, IA0 is unknown, the RA is given in the problem, it is 0.8 ohm. So, then the supply voltage is mentioned in the problem, it is 230 volt. Substituting all these values, we are going to get this IA0 as 6.25 ampere. So, this is the answer for the previous problem, that is 4 pole lap wound DC motor. So, next you see this, here we have changed something, here we are considering the two conditions. One at here in the problem they had given the two conditions, you have to analyze the data in both the conditions, substitute properly and use the required equations, substitute the values properly and get the proper answer. You see that in this problem it is mentioned it is a DC series motor, runs at 500 rpm on 220 volt supply. So, here I will explain to you how to analyze this problem. Here it is a DC series motor, means series field winding is connected in series with the armature. The supply voltage V is given to this. So, V is equal to, it is 220 volt. So, the motor is running at 500 rpm. This is motor, the terminals AAA. So, the motor is drawing a current of 50 ampere, and then the total resistance of the machine means they have considered the total resistance means RA plus RAC they had given. So, this is equal to 0.15 ohm. Totally they have considered this the internal resistance of the RA and then this is RAC. So, both they had given it is 0.15 ohm, and then calculate the value of extra resistance, that is Rx, to be connected in series with the motor circuit, that will reduce the speed from 500 rpm to 300 rpm. The load torque being then half of the previous value. So, now in the previous value when you are going to consider T1, in the second case it will be 0.5 times P2, because it is T1 is equal to T2 divided by 2, half of the previous value. Assume phi is proportional to current. In case of series motor, so we will consider always this phi is directly proportional to armature current IA. So, by using this data, now you find out what exactly we require. So, that is collect the data given, we have already collected, and then in this case when you are considering the series field is connected in series with the armature, the series field current is same as armature current. That is why phi is directly proportional to IAC, that is directly proportional to IA. We know that when we are going to consider this torque equation, that is TA is equal to 0.159 phi Z IA multiplied with P by A. Here number of poles are fixed, the number of parallel paths are fixed, here Z is fixed, 0.159 is a constant value. Now, TA is depending on what? TA is directly proportional to phi into IA, and in this case phi is directly proportional to IA also. So, since this phi is directly proportional to IA, we can say that T is directly proportional to IA square. So, there are two conditions. One is the speed at 500 rpm. When the speed change to that 300 rpm, you have to see that what resistance you are going to add, how much resistance you are going to add. So, it is T1 divided by T2. From this relationship we can get that T1 divided by T2 is equal to IA1 divided by IA2 whole square, because T is directly proportional to IA square. We have for the second condition, the torque is, see, the load torque being then half of the previous value, that is T1 T2 is equal to 0.5 times T1. So, T1 is equal to, so here T2 is equal to the torque in the second time, that is 0.5 times T1. So, that is why here T2 is equal to T1 divided by 2, means T2 is equal to 0.5 times T1. The torque at the second case is equal to 0.5 times the torque at the first case. So, substitute the value of IA1, IA1 is given in the problem, IA1 is 50 ampere. So, IA2 is unknown. So, now substituting these values, we are going to get this IA2 is equal to 35.355 ampere. Then use voltage equation to calculate this EB1. EB1 is equal to V minus IA1, since it is a series motor. So, you have to add that armature resistance and the series resistance. The total resistance is mentioned in the problem, that is 0.15 ohm. So, substitute this V is equal to 220, IA1 is 50, RA plus RSC is equal to 0.15. So, and when you are going to calculate EB1 is equal to 212.5 volts. Next, second case, here you have calculated this IA2. So, now you see that how much resistance you are going to add in series with the series field winding and the armature. Okay, I have considered this Rx is the extra resistance to be added. Then EB2 is equal to V minus IA2 RA plus RSC plus Rx. Where exactly you are adding this Rx? In series with this armature, you are going to add the Rx to reduce the speed. So, now what has happened here? All the three resistors are in series, that is RA plus Rx plus RSC, all are in series. That is why the voltage drop across all the three resistors you have considered here, that is multiplied with this current. So, now here EB2 is equal to, you are going to get this EB2 in terms of this Rx, and also we have the relationship, that is speed equation, N is directly proportional to EB by phi. Since this phi is directly proportional to current IA in series motor, so we have this N is directly proportional to EB and N is inversely proportional to IA. So, when you are using this equation relationship, it is N1 divided by N2 is equal to EB1 divided by EB2 multiplied with IA2 divided by IA1. So, now you have the value of N1, that is 500 RPM, N2 is equal to 300 RPM, EB1 you have calculated, that is 212.5 volts, and EB2 you have in terms of Rx, substitute that equation in this. IA2 you have calculated, it is 35.355, IA1 is given, it is 50 ampere, here in this it is mentioned. So, substitute all the values and only the unknown parameter in this is Rx, that is in this EB2 equation. Okay. Calculate this Rx, we are getting the value, that is 3.5225. What is the meaning of this? You are going to add the resistance value of 3.5225 ohm in series with the armature and the series field winding to reduce the speed of the motor from 500 RPM to 300 RPM. So, this is how you have to analyze the problem. Next, you see that one more series motor problem. Here, the series motor is having a resistance of 1 ohm. Between its terminal, it drives a fan. Here, I took this practical application of, it is this DC series motor is driving a fan, the torque of which is proportional to square of the speed. What is the meaning of this? Here, we are considering the relationship torque is directly proportional to square of the speed. At 230 volt, its speed is 300 RPM and it is taking current of 15 ampere. The speed of the fan is rise to 375 RPM. See, previously if the fan was running at the speed of 300 RPM. Now, you have to raise the speed of the fan to 375 RPM by the supply voltage control. Now, estimate that what is the supply voltage required to raise the speed of the fan from 300 RPM to 375 RPM. Here also there are two conditions. The supply voltage at 300 is given as 230 volt. Now, you have to calculate that what is the supply voltage at 375 RPM, that is the speed of the motor. So, collect the data given, V1 is equal to 230 volts. So, the total resistance is given, that is 1 ohm, and in the first condition the speed of the motor is 300 RPM. We know that in case of series motor, all the three currents are same because the armature, series field winding and the supply is connected in series. So, this is equal to, what is the given mentioned, it is 15 ampere and N2 is 375 RPM. So, now in case of series motor, we know that flux per pole is directly proportional to the current flowing through series field winding and also it is directly proportional to armature current. So, now we have the torque equation. So, according to torque equation, phi T is directly proportional to phi Ia. Since phi is directly proportional to Ia, you can consider T is directly proportional to Ia square. So, T1 divided by T2 is equal to Ia1 divided by Ia2 whole square according to this torque equation. Now, it is mentioned in the problem that torque is directly proportional to square of the speed. So, now you can consider this T1 divided by T2. T1 is directly proportional to N1 square, T2 is directly proportional to N2 square. So, you are getting this relationship, that is T1 divided by T2 is equal to N1 divided by N2 whole square. So, you equate this equation and this equation. Here T1 divided by T2 is equal to IA1 divided by IA2 whole square. Here it is there T1 divided by T2 is equal to N1 divided by N2 whole square. Equate these two, you are getting it is N1 divided by N2 whole square is equal to IA1 divided by IA2 whole square. So, now you have the value of N1, you have the value of N2. So, now you have the value of IA1, it is given in the problem. Now, you have to calculate this IA2. IA2 what we are getting is 18.75 ampere, and then here you have to estimate that supply voltage by using that current, okay. And also we have that speed equation. So, N is directly proportional to EB and inversely proportional to phi. We know that in case of series motor phi is directly proportional to IA, that is why we have that relationship N is directly proportional to EB and N is inversely proportional to IA. So, from this relationship we can get this N1 divided by N2 is equal to EB1 divided by EB2 multiplied with IA2 divided by IA1. Substitute the required values after calculating this EB1 and EB2. EB1 and EB2 are unknown, you have already, it is IA1 is mentioned in the problem, IA2 you have calculated, N1 and N2 you have. Now, the required values are EB1 and EB2. Use these voltage equations, that is EB1 is equal to V minus IA1. Since it is a series motor, the total resistance is RA plus RSA. So, V is 230 volt, the IA1 given is 15 multiplied with this 1 ohm, it is mentioned in the problem, you are getting this EB1 is equal to 215 volt. Similarly, you calculate this EB2, because EB2 you have to consider it is V2, it is the voltage is changing from V1 to V2, that is what you have to calculate, that is the aim of our problem. Estimate the supply voltage required to increase the speed of this fan from 300 rpm to 375 rpm. So, now EB2 is equal to V2 minus IA2 RA plus RSC. So, you know these values, when you are substituting it is EB2 is equal to V2 minus 18.75. So, substitute these values, then you are going to get this V2 is equal to 354.68.75 volts when you are substituting all the values in this equation. So, here only V is unknown. So, you can calculate V2 is equal to 354.6875 volts. This is the new supply voltage required to raise the speed of the fan from 300 rpm to 375 rpm. This is how we are going to analyze the data for particular applications, that it may be in the case of domestic application or it may be in the case of industrial application, whatever it is mentioned. So, we have to calculate and we have to analyze the data. Okay. Now, you see in this problem, the data given is, it is 220 volt shunt motor, means shunt field winding is connected in parallel with the armature. So, it is 220 volt shunt motor has an armature resistance of 0.25 ohm and the field resistance is 170 ohm. Determine the back EMF if the output is 4.5 kilowatt at 87% efficiency. This efficiency is a new word for you, because, so I did not use anywhere, but here whenever we are going to analyze any machine, we have to calculate that efficiency of the machine. Okay. Efficiency, we are using the symbol eta, that is equal to output divided by input. It is the ratio of output and input. So, whatever input, here you are going to consider this output divided by this input is equal to output plus losses. So, this losses include that copper and the frictional losses. These you are going to study when you are studying that AC motors. Here I am not going to teach this in detail. So, efficiency, that is equal to output divided by input, you consider this equation. So, now you see that how exactly you are going to calculate that back EMF when the output is given, because that back EMF also depending on the output. So, here collect the data given, V is equal to 220 volt, RA is equal to 0.25 ohm, RSH is given as, that is sometimes in the problem they will mention RSH with the symbol RF, then ISH with the symbol IF. It indicates that this is the field resistance and this is the field current. Since we have connected that field winding in parallel with or in shunt with that armature, we have used that RSH and then current flowing through, that is ISH. In some of the problems they will use this type of subscripts. Okay, it means that it is a field. The parameters are representing the particular field. Output power is given, it is 4.5 kilowatt, efficiency is 87%. I already told you that efficiency we are representing, it is the ratio of output and input. Now what is input? Input is equal to output divided by efficiency. Since it is given as 87%, 87% when you are representing, it is a value, it is divided by 100. So it is 0.87. 87% is represented as 0.87. So what is the input now? It is 5.170. It is more than this output because it has to overcome the losses also. So input is equal to output plus losses. So now you see that what is the input current? Input current IL is equal to input power is mentioned. So 4.5 kilowatt divided by the voltage, you are going to get that input current. Okay, it is 23.51 ampere. Then we have the equation for field current, ISH is equal to V divided by RSH. V is mentioned, it is 220 volt divided by 170, we are getting this 1.294 ampere. Then the armature current, we have the relationship, that is IA is equal to IL plus minus ISH, because in case of shunt connection, so what we are going to do, we are connecting this shunt field winding in parallel with the armature. So the current drawn by the supply, that is equal to ISH plus IA. So IL is equal to IA plus ISH. So now IA is equal to IL minus ISH. By using this relationship, you can calculate the armature current IA. So we are getting it is 22.216 ampere. Then use the equation, that is EB is equal to V minus IA RA. Substitute V, IA and then RA given in the problem. You are getting EB is equal to 214.446 volts. So that is the required value in this case. So determine the back EMF if the output is 4.5 kilowatt at 87% efficiency. When the efficiency is mentioned, directly use that it is efficiency is equal to output divided by input. Now in this problem, it is mentioned that it is a DC motor develops a back EMF. Back EMF is directly given. Okay, don't get confused with the supply voltage and back EMF. Back EMF EB is given, it is 220 volt at 1500 RPM. If the armature current is 50 ampere, find its mechanical power developed and the torque. I already told you that mechanical power developed is directly proportional to EB. So that is EB into IA, mechanical power developed, we can use this equation EB into IA, substitute the value, it is 11 kilowatt. Okay, and the torque equation in terms of this mechanical power is TA is equal to 9.55 multiplied with EB IA, that divided by the speed of the motor. The speed of the motor is mentioned 1500. So we are getting the value, it is 70.03 Newton meter. So this is how you have to perform the problem when they ask that mechanical power developed when the back EMF is mentioned. So now you see this problem, it is a DC shunt motor, it is supplying, the supply given to this is 220 volt and it is running at 1500 RPM. When the armature current is 50 ampere and the resistance mentioned is 0.112 ohm, calculate the speed. If the torque is doubled, here you see the condition, in each problem there is one data, it is different. So in this problem it is mentioned that calculate the speed if the torque is doubled. For the previous case, when you are going to consider, in the second case the torque is doubled. That is, the previous case if you are considering, it is torque is T1, in the second case when you are considering the torque is T2, so it is doubled means the second case the torque is twice the previous one, it is 2 times T1. Since it is a shunt motor, flux is always constant. since flux is constant in this, T is directly proportional to Ia. So, that is why you have this T is directly proportional to Ia. You have the two conditions, one is at torque T1, another one is at torque T2. Torque T2 is equal to 2 times torque T1. In the previous case, this current, armature current is mentioned, the Ia1 is equal to 50 ampere. So, now see that since the torque T2 is equal to twice, this torque is doubled, so T2 is equal to 2 times TA1. TA1 will get cancels out, 50, that is Ia1. Now, we have to calculate this Ia2. Substitute this Ia1 in this equation, calculate the back EMF EB1. EB1 is equal to V minus Ia1 RA, you are getting it is 214 volts. Ia2 what you have calculated in this, substitute in this equation, EB2 is equal to V minus Ia2 RA, you are getting back EMF EB2 is equal to 208 volts. And then we have this speed equation, N is directly proportional to EB by phi. I already told you that in case of shunt motor, flux phi is constant. That is why N is only directly proportional to EB. So, according to this relationship, N1 divided by N2 is equal to EB1 divided by EB2. You have calculated EB1, you have calculated EB2, you know the value of N1, substitute. Now, the new value of N2, that is the speed of the motor, is 1457.9 RPM. Now, you see this problem. So, what are the data given in this? Here, the number of poles mentioned is 4. It is the supply given to this shunt motor is 220 volt and it has conductors, 480 conductors, which are lap wound, means the number of parallel paths is equal to number of poles, that is equal to 4. It takes 50 ampere from the main supply and develops an output power of 6.2 kilowatt. The field resistance is 220 ohm. The flux per pole is 30 milliweber. RA is given, it is 0.15 ohm. Now, we have to calculate back EMF, speed and shaft torque. I did not do any of the problem on this shaft torque. In this, we are aiming to calculate this shaft torque. The data given is V is equal to 220 volt, P is equal to 4, Z is equal to 480, the number of parallel paths A is equal to 4, the current drawn by the motor is 50 ampere, RSH is mentioned, it is 220 ohm, the flux given is 30 milliweber, 30 into 10 to the power minus 3 Weber, RA is equal to 0.15 ohm, output power given is 6.2 kilowatt. This is the shunt motor, is what I have already considered in this. I told you that this armature is connected to the shaft. So, whatever the TSH we are getting is always less than TA, because the armature torque, the torque developed at the armature is not fully available at the shaft. It is always less than this TA. Okay. This is the shunt motor. So, when we are going to apply the voltage V, the current is supplied to the motor, the current drawn by the motor is IL, and then IL is equal to IA plus ISH. Okay. Here the back EMF EB is induced in this. So, we are mentioning here the resistance RA, because this is the internal resistance of the motor. So, since the field winding is connected exactly in parallel with the supply, ISH is equal to V divided by RSH. So, both the values are same, that is why we are getting this 1 ampere. So, from this equation we know that IA is equal to IL minus ISH. Substitute the values, IL is mentioned, it is 50 ampere, ISH calculated is 1 ampere. So, we are getting this is 49 ampere. Now, what are the required values in this? Back EMF, speed and shaft torque. So, now we have the equation for EB, that is V minus IARA. Substitute V given, that is 220 volt. This IA is calculated 49 ampere, and then this RA is mentioned, it is 0.15. So, substituting and calculating, we are getting EB is equal to 212.65 volts. So, we are getting this EB. In the second part, we have to calculate the speed, and we have one more equation, that is EMF generated EB is equal to Zn 5P divided by 60A. Here EB is directly proportional to speed. Okay. So, substitute EB whatever you have calculated in this, it is 212.65, number of conductors are mentioned, Z is equal to 480, and then phi is mentioned, it is 30 milliweber, 30 into 10 to the power minus 3, and then the number of poles are mentioned, P is equal to 4. So, divided by 60 into, here it is mentioned it is lap wound. In case of lap wound, the number of poles is equal to number of parallel paths is equal to 4. So, that is P is equal to A is equal to 4, it is given in the problem. Okay. Substitute. So, you are going to get this N is equal to 886.04 ampere. And we have the equation for this shaft torque, TSH is equal to 9.55 into, that is output divided by N. So, output is mentioned in the problem. You see this motor is of output power, it develops an output power of 6.2 kilowatt. Kilowatt means it is 10 to the power 3 watt. 6.2 into 10 to the power 3 will be 6200, that is divided by this speed calculated 886.04 RPM. So, it is 9.55. Okay. So, 9.55 into 6200 divided by 886.04. This is equal to 66.82 Newton meter. By mistaken here I left this point, it is not 955, it is 9.55. So, after calculating you are getting it is 66.82. This is how we have to do the problems. So, today I am going to conclude this DC machine. Okay. So, when you are analyzing the problems, first you should see the data, read the problem thoroughly, see that what type of motor it is mentioned and what are the data given. You collect all the data given properly, and then you think that what are the equations you have to use, substitute the values given in the problem and get the required value. Okay. So, now you have studied this all the working principle. This first you have seen that the construction of DC machines as generator and also as motor, and then working principle of generator and working principle of motor. So, in case of this working principle of generator, we have considered that Fleming's right hand rule. In case of motor, we have considered Fleming's left hand rule, and also we have used that electromagnetic induction properties, that is Faraday's laws of electromagnetic induction, Lenz's law. Okay. So, by considering all this, you have studied the working principle of DC machine as a generator and motor, and also you have studied the characteristics of motors. We have derived the equation of back EMF for generator, and also we have seen that what is the equation of back EMF in case of motor. So, and also we have derived the equation of torque developed at the armature and torque developed at the shaft. We have solved so many problems on this generator and motor. I think you are comfortable with this DC machine, that is module 2 DC machines. Okay. So, the outcome of this topic is, after studying this DC machines, after the completion of this module about DC machine, the student should be able to select the type of generator or motor required for a particular application. In the last class, along with that characteristics, I told you that what are the applications of series motor, then shunt motor, compound motor, that is cumulatively compound motor and differentially compound motor. Okay. And also I told you that what are the applications of generators. Okay. So, I think now you are able to decide what type of generator and motor is required for a particular application. So, in the next class I am going to start measuring instruments. In that you can study that wattmeter and also the energy meter in detail. Okay. Thank you.